I'm warmly welcome everybody. My name is Noemi Sarkadi. I come from University of Pécs from Hungary. And first of all, I would like to say thanks to the DTC program because I'm a visitor related to the DTC visitor program, and I'm worked on towards improving high-resolution numerical weather prediction, especially in the case of convection by using a bin microphysics scheme. During the presentation, first of all, I would like to give you a short overview of the detailed microphysics scheme that I used, and I will show some results. Briefly, I will talk about an idealized 3D scoreline simulation. It was the 2012 cloud modeling workshop case, and also a real 3D case study related to the 2016 cloud modeling workshop. Then I will conclude and summary the results, and I will talk about a little my further plans. So usually in numerical weather prediction models, there's in operative forecast using bulk microphysics. In this case, the bulk microphysics main assumption that they have a function to describe the size distribution of the different particles, like cloud water or raindrops. And with this, it's really good for computation time because it's not costly, but there are some disadvantages related to the bulk microphysics, that some of the size-dependent properties, like the size-dependent vertical terminal velocity of the particles, are not easily calculated. Compared with the bulk microphysics, there's a second chance to describe microphysics in numerical weather prediction models. This is the bin or detailed microphysics scheme. In this case, the whole size distribution we divided into small size intervals, and all the intervals, the mass and the concentration of the different particles are calculated. The advantage of this description is we are able to describe the size-dependent terminal velocity and also a correct description of collision coalescence effects between the particles. The disadvantage of the bin schemes that they are really expensive in using this in weather prediction models. In our scheme, 4 different types of hydrometeors were divided into 36 bins. These are the pristinized crystals, the water drops, which at the end we can separate it to cloud water and raindrops, snowflakes and graupel particles. The number of the calculated variables is over 400. It means that for all size categories and for all particles, the mixing ratio and the number concentration are calculated, and also in the case of the snowflakes and graupel particles, the mass of the melted water is a prognostic variable, and also related to the rhyming effect, the rhyme water number concentration and mixing ratio is also a prognostic variable in our bin scheme. The melting fraction and the rhyming fraction are 2 diagnostic variables that help us to move or describe that how our snowflakes and ice particles are melted. So if this fraction is over 80%, we move to the snowflakes and graupel particles to water drop category, and also if the rhyming fraction is over 50%, the snowflakes just transfer to graupel particle. The following microphysical processes were taken into consideration in our model. All the different microphysical processes like melting, freezing, or condensation, evaporation, just like rhyming, or the breakup of the water drops. It's really, I would like to point that in the past 1 year, a collision-induced shedding process were developed or introduced to the beam scheme. It's really similar to the bar scheme shedding thing. It means when the snowflakes or dropper particles are partly melted, in bar scheme usually the melted water just shreds from the surface of the particles. In our scheme, they shred if they just collected with the water drops, so it induced the shedding. If they are not collide with the water drops, shedding not occur just above a critical size. And now I would like to talk about the case study. So scholines and convective cases are really sensitive of the description of dynamic microphysics interactions. So the accurate forecast of these type of weather phenomena is really important. In this idealized 3D scoline case, we used a 1 kilometer horizontal distribution with 100 vertical levels. All the radiation and planetary boundary layer effects, also surface atmosphere interactions were neglected. We used beam microphysics during a 10-hour simulation period, and the initialization of this scheme of this simulation, we used theta perturbation and horizontal wind convergence in the middle of the domain. I just show some results briefly. On the left side, there will be a horizontal cross-section of the calculated radial reflectivity, and on the right side, the vertical cross-section of the calculated radial reflectivity. In our case, you can see how the scoline moved forward and how formed a bright band. In this case, the transition zone of a scoline wasn't so well defined, just in some parts during the simulation, you can see here. And also there is a bright band, but not so well defined bright band as usually we accepted. In this case, really interesting how the temperature changed during the simulation, because in the case of a scoline, the decrease of the temperature due to the evaporation of water drops and also the melting of snowflakes can, it's really important to propagate the scoline above. So it's also the same horizontal and vertical cross-section of the temperature change during the simulation compared to the original. You can see here how the cold pool formed below the stratiform region. Also, the real inflow is also here, and during the whole simulation, it's about minus 10 degrees, the change of related to the original or the initial temperature change. But I think the most important and interesting part using beam microphysics is we are able to describe and measure the size distribution of the different water drops. In this case, I separated for the 8-hour simulation. This is the water drop size distribution in different levels. At the surfaces in blue, at around 11 Celsius or 2,200 meter high, and at around 5 degrees is the red line. There's 3 regions in this case: the stratiform, the transition zone, which I mentioned wasn't so definite in this case, and in the convective region. If you compare the stratiform region size distribution, just see at the surface the blue lines, and the convective region, you are able to see that in the convective region related to the updraft and the activation of the CCN, small water drops are formed, and the larger ones related to the melting of groundwater particles, which terminal velocity was enough high or large to fall out in the updraft region too. In the case of the stratiform region, the small water drops just evaporate during their falling down to the surface, and they are usually formed due to the melting of snowflakes. If we compare the calculated and the measured median volume diameter, I'm not sure you can see it, they are pretty close to each other. I just give an interval because it's somewhere in between. So in this case, our calculated median volume diameters agreed well with the measured median volume diameters. So it's really important. It's something that should be taken into consideration in the future, also when you're using a bulk microphysics scheme, that maybe in a scoreline simulation or a convective case, using a different parameters for describing the size distribution of the water drops is important for the accurate precipitation forecast. And now about the real 3D simulation. I think we were the first one who's using a beam scheme in a real case study. It's a convective. It's related to 2016 cloud modeling workshop case. It was a COPE study, which is a convective precipitation experiment in southwestern England. In this case, it was in 2013, the 3rd of August. It was an intensive observational period. In this case, 2 convergence lines formed parallel to the coastline of southwestern England and start to developing convection and cumulus clouds. In this case, was the main question how ice processes and ice formation, especially ice multiplication, play role in the formation of precipitation in the ground. In the measured and the simulated case wasn't so intense, but previously similar conditions, flash floods also developed due to the high amount of precipitation in this region. So they are using this time period. The August 3rd case was a well-manageable and organizable case because it has a well-defined sea breeze flow, so all the measurements could be managed. In this case, I used Weather Research and Forecast 3.7 version. The initialization was from GFS data from 3 kilometer coarse grid nested to 600 meter. We used almost constant CCN, which is described by maritime conditions, but in this case, also RSO measurements are available. We used RRTMG radiation scheme code in every 15 minutes, Money-Nabokov stream, and unified NOAA land surface model to describe the surface layer and land surface options, and YSU seam to describe the planetary boundary layer. I made 3 different, little different simulations with the dynamical, and the model setup was almost the same. I just changed the microphysical processes. So the horizontal resolution was 600 meter with 71 vertical levels up to 20 kilometer. It was a 12-hour simulation from 6 a.m. to 6 p.m. with 3 seconds of dynamical time step. And the changes, the first column shows the control case. In this case, all microphysics were taken into consideration with Cooper ice initiation process. There was a second also with Cooper ice initiation, but without the Halep-Mossop ice multiplication process. So I turned off the Halep-Mossop effect. And the third one is with all microphysics, but using a different, the Demott et al. 2010 ice initiation description, with using a constant 1 per cc aerosol concentration. So just look at the results. Oh, before that, I just would like to show you the simulated domain. In the further pictures, I will focus on this northeast part of the domain, because here occurred the convection, and this is a high resolution MODIS image for that day. You can see the nice convergence line with convection. So about the precipitation, in all cases, if I have the control, the case without Halep-Mossop, and the Demott, this will be the order of the images. So the first is the control, the second is the Cooper ice initiation without Halep-Mossop effect, and the third one is the Demott with the Demott ice initiation. If we just check the total domain integrated precipitation, in the case of the Demott and the control, are really close to each other. And if we compare the 2 pictures, they are really similar, but also the without Halep-Mossop is also similar to the distribution of the precipitation in the ground, but in this case we have more precipitation. I will give you some explanation in next slides later. If we just check how changed the Halep-Mossop effect of the surface precipitation, you can see the difference between the control Cooper and without Halep-Mossop ice initiation. And the blue colors means that in the case of without Halep-Mossop, we have more surface precipitation compared to the original or control case. Every time I show you the 3 p.m. results, because I have measurements related to this time period. If we just compare our simulations with observations, so the red line shows the radar integrated domain mean precipitation, the black line shows the control Cooper, the dark blue is the control Cooper without Halep-Mossop, and the light blue shows the Demott results. All of the beam results are really close to each other, how the curve shape changed during the simulation. It's a little far from the observation, but in this case the observation and the simulated domain size wasn't the same, so we are still focusing to fix it and have related observations to our simulations. it's really important that after 3 hours simulated time, we have precipitation on the ground with the bin microphysics scheme, which is compared with the back results. They do not have it, so it's something that the bin scheme gives precipitation after a few hours instead or against the back scheme. I think this is related to the description how the hydrometeors fall out in the bin scheme. So the larger water drops or formed group-up particles are fall out earlier in the bin scheme instead, while during using a bar scheme, they do not fall out because they do not reach the mass-weighted terminal velocity. If we compare our results, this shows the 3-hour calculated radar reflectivity in the control without Halep-Mossop and with the DEMOT ice initiation. In this case, you can easily see some differences between the different simulations. In the case without Halep-Mossop effect, we have more separated and more, I think it's easy to see the cells, and they have higher reflectivities compared to without the with the Halep-Mossop effect. I think it's related to how the microphysics work in the case without Halep-Mossop. But also we can compare it with measurements. This is the measured radar refractivity field. You can see that the location of the convergence line is really close to the observed one, but at the upper part there's some shifting. Maybe I think the modeled clouds are a little further northeast than in the case was it measured. And also, I think in this case, the DEMOT are closer to the observations than the other simulations. If we compare the column maximum radar reflectivity frequencies, also the red line shows the observations, the black is the control Cooper, the dark blue is the Cooper with without Halep-Mossop effect, and the light blue is the DEMOT case. In this case, for high reflectivity, low frequencies, the control is really close to the observations, but also you need to take into consideration that it's still not the same domain that we use for the observations and for the simulations. But you can see that the DEMOT case are closer to the observations at low dBz high frequency values. In this case, it was important how the ice or ice multiplication are interact or play a role in precipitation formation. So I just compared the average mean ice number concentrations, average between -3 and -8 degrees, which is the region of the Halep-Mossop effect. And you can see that between the control and without Halep-Mossop effect, we have more pristine ice crystals in this region, which is, of course, because in the no HM, we are just turned off the Halep-Mossop formation. If we just compare the control and the DEMOT case on the left-hand side, you can see all these light greens and light blues and dark blues shows that the DEMOT has more pristine ice in this region than the Cooper gives us. Also, both of them use the Halaf-Mossop multiplication effect. If we check how it affects the rain, the snow, and the grouper formation near to 0 degree, you can see that in the control case we have more snow, and also we have more grouper, which is these yellow and reddish colors shows that the control has more grouper. It's really important because without grouper particles, no Halaf-Mossop can occur, because it caused due to the collision with grouper particles and water drops. So when they collide, small pressurized particles and chunks can form due to this effect. And also we are able, it's a little busy figure, so I will just give you some explanation. This is the size distribution at the point where the case without Halaf-Mossop has its maximum surface precipitation. The first column shows the snowflakes and snowflakes rhyming. The dashed line shows the rhyming fraction. The second column shows the snowflakes and melting of snowflakes. The third is the grouper size distribution and the melting of grouper particles. Because the dashed lines are close to 0, it means there's no melting. It's around -5, close to 0, but still in the negative temperature. It's the second row, and the third row is around 2 Celsius. The fourth is the water drop size distribution, and the fifth column is the ice crystal number concentration as a function of the size. You can see that in the case, I just would like to point out some parts that we have at -5, which is the middle of the Halaf-Mossop region. We have lots of ice crystals formed due to this effect. And also you can see that in the case of without Halaf-Mossop, we have higher number concentrations of the larger water drops that can cause due to less grouper particles and no snowflakes, so only the water drops and grouper particles are racing to collide or collect water drops in this part, so larger water drops can form, they are fall out and cause higher precipitation on the ground. So maybe this is one of the reasons why without Halaf-Mossop effect we have more precipitation on the ground. This second picture shows the size distribution of the same height and also the same all the columns, where the snow number concentration difference is the highest between Halaf-Mossop and without Halaf-Mossop cases. You can see that in this case some snowflakes are also occurred, but without Halaf-Mossop we have less snowflakes, and in lower altitude we have smaller snowflakes as well. But also in this case we have more water drops formed due to the melting of particles and collision between water drops, so self-coagulation. So summary, related to the idealized skull line case, I think the most important finding was that the size distribution of the water drops differs between the convective and in the stratiform regions. So to describe this difference in bulk scheme can improve or may improve the scoreline simulation, and also an accurate forecast. In the 2016 real case study, without Halep-Mossop effect, we have better agreement with the measurement in the amount of the precipitation, but the radar measurements are really close to each other in all cases. It's something a little maybe confusing, but we are still working on this project, so we need to check more detail of the results. So this is our further plans. I would like to publish both of the idealized and the real case studies, and also in the idealized scoreline, some measurements are available, so more detailed comparison with those measurements are needed. And also in the case of the COPE study, the simulated and the observed particle size distribution should be compared. Related to the COPE case study, where aerosol measurements are also available, so it's really important to implement the aerosol concentration and aerosol effects to the beam scheme to describe better the aerosol cloud interactions between in a cloud, how they play role in precipitation formation. And also in our really further plan is to implement and make it public the beam scheme in the newest version of the VERF. So I would like to thank you for your attentions, and if you have any questions, just feel free to ask me. Thank you. Yeah.
Did you run did you compare your results with bulk microphysics?
Yeah, we are still working on it. I have just some preliminary results from the BAO schemes, but some of them are using pretty different initialization processes, so we need to compare it in more detail. But the first result shows that it was really important that in the case of the BAO schemes, if they turn off the Halep-Mossop effect, they do not have so huge effect on the precipitation that we are using with the beam scheme. So it really need to just investigate what caused this difference between the BAC and the beam scheme.
And how much adds the beam microphysics computationally to a comparison with the bulk scheme?
Oh, with the BAC scheme it's around 2 hours, and with the beam scheme it's around 12 days.
Okay.
Yeah. Yeah.
There is a beam scheme in WRF, right? So you compared your beam scheme to?
Not yet. Do not do it, but I think Lurin Shu did some comparison between the two different beam schemes. In
Three different beams.
Three.
Three different.
Okay. Yeah, he did, but I never checked the difference between the beam schemes. Yeah.
Do you have CCNs as a prognostic variable? You didn't list it.
Oh, we just use the CCN as maritime or continental, so we can switch between them. But it's just described as how they initiate the formation of water drops. So they are not really prognostic variables. They are just something depend on the temperature or the saturation, how they initiate the cloud water. So that's why I think implement something aerosol and the cloud interaction to the scheme is it would be nice. And my supervisor, now he's my boss, is working on István Geresdi. We have a different set of bin microphysics with RSO, including, but just with warm rain processes, so it's not a full developed bin scheme. Yeah.
Thanks for your talk. So I'm interested in part of your aerosol cloud interactions, the plan. So in addition to the aerosol size distribution to be verified, do you want to consider some aerosol species or the process on the ice nucleation? Because I heard
First, yeah, but our further plan to have a full set of detailed aerosol cloud interactions. As I mentioned before, we have a warm rain process including bin scheme with 55 beans for our aerosols and also 36 beans for water drops, and it's worked pretty well, but need to implement the ice processes to having a full set of aerosol cloud interaction in our bin scheme.
So I have another question.
Okay.
You output your simulations in 3 seconds. Is there any reason that you do that? Because from the comparisons, I didn't see any verification based on such high resolution. So
I'm not sure that I really knew or understood your question. So, yeah, you mean that how related this whole thing to high resolution forecast?
I mean, you output your results in 3 seconds, right?
Yeah.
In your simulation. Is there any specific reason that you do such?
Everybody used that, so that was the only thing that I initiated the bin scheme from the course grid. We used just bar scheme, so and because we would like to make it compare, I just did not change it. So I just used the same like in Greg Thompson in his scheme.
But in the comparison with the observations,
yeah.
the resolution is not so high, right? The temporal.
Yeah, but you mean, but it was the dynamical time step, but the output time was 15 minutes. So I have results in every 15 minutes.
So I got it wrong.
Yeah.
Thank you.
Okay. Yeah.
Can you go into a bit more detail about why you think that the simulation without the Hallett-Mossop effect produced so much more precipitation? I may have missed that part.
Yeah, I think due to we have less graupel and snowflakes in the case without Hallett-Mossop effect.
Sure.
And because of it, the available cloud water are just when they are colliding or collide with each other, they form water drops. So there's no snowflakes who collecting also those water drops. So in this case, larger water drops can form and they fall out faster. So that's my thinking, but I need to check the results. Some of them just finished on Wednesday, so I'm just trying to do my best with these plots. So
thanks.
You're welcome. Okay, thank you very much again for your attention.